Welcome back. In Part 2, we analyze the technologies organizations currently use to move files and examine why traditional methods break down in large-scale environments. Chapter 6 focuses on the File Transfer Protocol, or FTP, which is the most widely used, yet most misunderstood protocol. FTP was designed in the 1970s primarily for exchanging files between research institutions in limited network environments. Importantly, security was not a primary design goal. Today, FTP is used in environments far larger than it was designed for, including financial systems, manufacturing facilities, and large-scale data collection. FTP was not originally designed for this scale. One of the biggest issues is security. Default FTP transfers data in plain text, meaning file contents and user credentials are not encrypted. While security extensions like FTPS and SFTP exist, they are added layers, not original features. Security extensions often create operational complexity, making firewall configuration more difficult and leading to issues like NAT conflicts and passive mode. FTP treats security as an afterthought, which conflicts with modern requirements. FTP operates using a session-based model: connection, authentication, file transfer, and session termination. This structure works for a small number of systems. In large-scale environments, hundreds of devices connect simultaneously, rapidly increasing session counts and server load. This leads to timeouts and session crashes because FTP was not designed for this scale. The retransfer cost is another major issue. If a 50 GB file transfer disconnects at 90% completion, the entire file must be retransmitted, wasting 45 GB of already transferred data. Next, we move to Chapter 7, focusing on SSH-based transfers, which are more secure but still limited in large-scale environments. SSH-based tools like SCP and RSYNC offer built-in encryption and strong reliability, especially in Unix environments. RSYNC is particularly useful for incremental transfer, only moving the parts of a file that change. RSYNC's strengths lie in efficient incremental transfers, reliable file synchronization, and simple command line automation. These advantages primarily apply to small or moderate environments. The main limitation is that RSYNC is a tool, not a centralized platform. Large environments require manual management for script creation, key distribution, log monitoring, and error handling. Operations become script-based management. When dealing with hundreds of production devices, operational tasks multiply, including device-specific scripts and failure recovery logic. The operations team ultimately becomes script managers. The accumulation of operational fatigue is a consequence. Large environments generate thousands of log files, and failures on a small subset of devices require root cause analysis and manual retransfers, leading to increasing strain over time. The real lesson is that script-based automation is not true automation. It becomes distributed management, with manual interpretation of logs and increasing operational burden. Large environments require centralized transfer architecture. We move now to Chapter 8, which explores the impact of the wide area network environment and round-trip time, or RTT, on file transfer performance. RTT means round-trip time. It measures how long a packet takes to travel to its destination and return. RTT increases with geographical distance, significantly reducing transfer efficiency in traditional systems. Traditional transfer tools use a sequential model: send a packet, wait for a response, then send the next packet. In high RTT environments, this causes latency to accumulate, resulting in actual transfer speeds far below theoretical bandwidth. WAN environments require parallel transfer structures. Files are divided into segments and transferred simultaneously. This maximizes available bandwidth, reduces the effect of RTT latency, and improves completion time significantly. Chapter 9 addresses structural problems in large-scale file environments, moving beyond network issues to focus on challenges related to file volume and size. Extremely large files, sometimes tens of terabytes, introduce key technical pressures, including disk I/O bottlenecks, increased memory consumption, and high retransfer costs if interruptions occur during long transfers. Very large file counts, such as environments generating millions of files, create different system pressures. Key challenges include heavy metadata processing, increased file open and close operations, and synchronization complexity across systems. Chapter 10 discusses failure scenarios from an operational perspective, where failures are inevitable, and efficient management is critical for large deployments. In large deployments, partial failures, where only a small subset of devices fail, create large operational workloads. Manual recovery involves identifying failed devices, analyzing the cause, manually resending the transfer, and verifying completion. Manual log-based analysis is a limitation. In large environments, thousands of logs must be read and interpreted manually. As log volume increases, troubleshooting becomes slower, requiring automated detection and recovery. Chapter 11 covers cost structure analysis, urging organizations to look beyond direct technical costs to evaluate the full operational impact of file transfer systems. Many hidden costs accumulate in file transfer operations, including staff time for preparation and failure response, retransfer costs, and the maintenance of intermediate servers. These factors significantly increase the real cost. Transfer systems should be evaluated using total cost of ownership, or TCO, which considers the long-term operational impact, workforce requirements, and the complexity of maintenance and failure management. Automation dramatically changes the TCO structure by reducing operational workload, simplifying system management, and improving long-term efficiency, turning it into a strategic improvement. We conclude Part 2 by noting that traditional transfer tools are insufficient for enterprise scale. A dedicated transfer architecture is needed to handle hundreds of devices, dozens of terabytes, WAN environments, and continuous automation.